Hi everybody. Today we're going to go through is some definitions, so mostly definition based. I don't think I have that many examples, but we're going to look at some subspaces, and obviously what we're going to see is that if we want to define subspaces, we will have to define some vector spaces, which would be like the parent class of that. So let's jump in with, we're going to look at our definition of subspaces and see where we hit a wall. All right, so on the screen, don't rush to copy this down. We can see that a subspace, let's call it U, is a special type of subset. Now, some of us don't know what a subset is, or what a set, obviously a subset is a part of a set, but some of us are going into this not knowing what a set is. So if you do, you can probably skip some of this, but if you don't, let's jump right into that. And it might still be a good refresher, even if you already know what they are. All right, so this is more of a prereq thing, but we're going to look at what are sets and subsets. So let's get some definitions down. So a set is a group of, of elements. And that means you may ask from that is what is an element? An element is an object in a set. And it's usually, that object is usually a number, rather. So you can have a set of random sets, can be anything. You can have like a paper bag. I don't know. You can have a paper bag with a red ball and a blue ball and a green ball, and that would be a set. And then I'll come back to this later. So every ball in this paper bag is an element of this set of bouncy balls. You can have a set, you can define them, you can make them whatever you want. Let's say I have a set of 2 and 3, that is a set. Or there's some like special sets. One that we look at a lot in linear algebra is the real number set. And then there's some other sets. You have the complex number set, which we will not be covering, hopefully. And we have the integer set, which is Z, and there's the natural numbers, I forget the letters, but mostly we're going to focus on the real numbers here, and then a lot of them will be integers. All right, so a subset, actually before that, the symbol here under element, that means is an element of, so it's part of the set. So notice an example from math class. Let's say you solve for something and then you write x is an element of the real numbers. So you're using x is part of this. X will be a part of this set of all the real numbers. So that's what that means. And then with this example, I can say that 2 is an element of the set 2 and 3. And if I use the paper bag, purple ball is an element of the set of the brown paper bag. I'm just gonna whatever. All right, so subset. So we know that a vector subspace is a special type of subset, but what is a subset? All right, so okay, after that, so with the subset, a subset is defined as any collection of objects from a larger set. So if I have that down, so any collection of objects from a larger set. So one thing to note here is that the original set itself is a subset of itself. So if I take my example of 2 and 3, so 2 and 3, and I use the subset symbol, 2 and 3 is a subset of 2 and 3, which is something that is important to remember. And if I use our number groups again, the integer numbers, I think that's Q, is also a subset of all the real numbers. And then if I take red ball or purple, red ball and purple ball is also a subset of the paper bag. Okay, let's move on to some lineage stuff. So, a subset. So if something is a subset of another set, that means everything that's in the subset is also part of the bigger set. And now we're going to look at what if the set is a vector space, but also what is a vector space. All right, so let's have a look at what makes a set a vector space. And then from there, we can define subsets of the vector space, which will be then subspaces. All right, so now on to some lineage stuff. A vector space is a set of objects where 10 properties are met, but especially these two. So we have closure under addition and closure under multiplication. So most of the 10 rules, they're called axioms, can be like encapsulated into these two. Let's see. All right, so if you add two things of the same type together and the sum is still the same type of thing, then it's closed by addition. So if I add two real numbers together, the sum is still a real number. That means that R2 and R3, for example, are vector spaces. And if you define something that way, and then for any addition together, it's still the same type of thing, it's closed by addition. All right, so closure under multiplication is when you multiply a certain type of object by a real number, and the product is still an object of that type. So if I multiply a vector, if I scalar multiply a vector in R2, it's obviously still going to be a vector in R2, no matter what that number is. Whether it's 0, a negative number, it's still in that space. So that's why R2 is a vector space, for example. All right, so if both of these are true, then we have a vector space. Because I know I said there's 10 rules, but basically most of the rules can be checked by checking these two. All right, let's keep going. So we're going to move on and go look at some background information here. So why are we learning this? So let's look at some real vector spaces. So you're probably already familiar with vectors in R2 and R3, and to you, they're arrows in 2D and in 3D respectively. Within your past experience, we've also used coordinates in the appropriate number of dimensions, which let us write vectors in R2 in a few different ways. So we have our standard basis vectors I and j. We can write them as the coordinates of the position vector, or vertically as a column vector, which helps us with our matrix math. They can also be described geometrically. We're going to skip that for now. This also let us write vectors in R3 as ordered triples with your ij and k, ab's with our vertical and our horizontal vectors as well. So now we're learning that we can apply this knowledge of writing our vectors out like this to the nth dimension. So this can keep on going for like an incredible amount of numbers. So because it's just a list of objects. So we can do this with infinitely many dimensions as well. That's what we're learning right now. So this means we can write any ordered n-tuple, so like an ordered double, ordered triple, ordered quadruple. N-tuple is just like it's a generic version of that word. So we can write any ordered n-tuple of real numbers as a vector. So that might be new. So basically we're extending the definition of a vector even further. So, but they do have to follow the 10 rules called axioms, and we just have to check the 2 of them that we mentioned. So the big idea is that this means that any list of things that meets the 2 big rules we discussed earlier, that can be considered a vector. So it can actually be like vectors themselves in really big dimensions. It can be matrices, and it can be functions. But for our purposes, we'll just focus on some vectors. Excuse me. And oh yeah, that's what I just said. Okay. Let's move on. All right. So now that we know what a vector space is, what is a subspace? And we'll have a look at that. All right. So let's remember that the vector space Rn is closed under addition and scalar multiplication. So remember that when we have both addition and scalar multiplication, that means if we combine those together, this process is known as a linear combination. So that's your C1 V1 plus C2 V2 plus yada 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 plus Cn Vn. This, oops, that's an n. So this combines, obviously, addition, but it's also scalar multiplication. So that means that, that means that for any linear combination, the result of this linear combination is still going to be, part of Rn. Okay. Because it is closed under addition and scalar multiplication. When we have both of these, that means that we can have linear combinations. Okay. All right, so, and remember that a subset of Rn, or any big set, is any collection of objects of Rn or the big set. So we're going to look at special subsets of Rn that are also closed by linear combinations. So that means that there's no bound, that if you do linear combination within the subset, it will still be in the subset. And then anything in the subset, when we did our little review of set theory, anything in the subset is in the bigger, anything in the subspace will be in the overarching vector space. Sorry. Because anything in a subset is in the big set. All right, so definition: a subspace U is a special type of subset that meets the following conditions. The zero vector is an element of the subspace U, so that means that basically U contains the zero vector of n dimensions. So whichever dimension it is, if it's in R2, it'll be a vector with 2 zeros. If it's in R3, we'll have a vector with 3 zeros. Blah 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 blah. We're not talking about matrices right now, but if we have a 2x2 matrix, then this would be a 2x2 matrix with all zeros. That helps us meet the conditions for that. And then it's going to inherit the rules from the big set. So for any 2 vectors in the subspace, the sum of those 2 vectors will still be in the subspace. So it follows the closure by addition rule we covered earlier. And then for any vector in the subspace, and then we have any scalar k that is an element of the real numbers, that means that if we multiply them together, the result of the product will still be in the subspace. So that means that it inherits the scalar multiplication closure property. All right, let's try to visualize some subspaces. So since the subspace contains a zero vector, and that means like at the origin, it must pass through the origin, because obviously the zero vector is the origin. If I take the point in R2, this is just the origin in R2. If I have the origin in R3, this is just, how do I draw this? The origin in R3. So if the subspace, if the subspace has to contain this vector, then it has to go through the origin. So this is not a subspace in R2. This would be, because it goes through the origin. That's assuming that the lines I drew were straight. Because so it has to extend infinitely in all positive in all possible directions away from the origin. And one thing I forgot to write, since we looked at linear combinations only, these are like straight things going through the origin. So that means that nonlinear things are not subspaces. Oops. So in R2, we would have a line going through the origin, and that would be a subspace. So that would, let's say this is subspace U, it would be a subspace of R2, and then if I have R3, this would be a plane or a line through the origin because the dimension of a subspace, so it goes through the origin. I don't know how to show that. The dimension of a subspace has to be less than or equal to the dimension of the vector space. But also a line through the origin is also a subspace for R3. So U is still a subspace in R3. And then let's call this little highlighter thing W is a subspace of R3. But if I had this curve or like a circle or anything that's not linear, obviously that's not really possible with linear combinations, so it's not a subspace. All right, and then there's some part of it, some linear combinations will get off the curve, which is why that doesn't meet the requirements. So I would jot that down. All right, so a proper subset or a proper subspace is when a subspace isn't just the original subspace. So if we go back to the original, so let's say I have this set, like this applies for sets and subspaces. So this blue, or it's going to turn purple in a bit, or I don't know, that is a proper subspace. However, because it doesn't include everything. However, if I do this, this will not be proper subspace because it's just everything again. So remember that R2 being a subspace of R2, actually, I think I have the symbols mixed up, but whatever. I don't know what the line means. Okay, whatever. But if R2, so R2 is a subspace of R2, but it is not, let's write this out again. So R2 is a subspace of R2. However, it is not a proper subspace. So that's just a random definition we have there. All right. I think we have one more thing. All right, so let's look at the dimension of a subspace. So we can remember that the dimension of a vector space is going to be equal to the number of coordinates. Oops, I'm missing a letter. So we've chatted about this before, but for R2, oops, the 2's like up here. It has two numbers in it, so that means there's two coordinates in every vector in R2. In R3, there's three coordinates. So notice in 2D vector space, there's two dimensions, or there's two coordinates, and then in 3D vector space, there's there's three, sorry. My bad. So, and also, if I have a matrix, we have 2 by 2, and that means there are 4 numbers inside the matrix. So, and that applies to matrices of all sizes. If we multiply the dimensions, we can find how many numbers there are inside, which is kind of obvious once I say it. So if we have this, so we notice that so let's have a definition for the dimension of a subspace. So if W is a subspace of V, so if W is a subspace of V, I don't know if that makes any better because it's not very legible, then this implies that the dimension of W is less than or equal to the dimension of the big vector space. So if remember that we just did, like, a line through the origin is still a subspace of R3. So the dimension of that line is 2D, and then is 2, because you need two vectors to make it, and then R3 has 3 dimensions, so that means that this holds true. So for the case where if the dimension of the subspace is equal to the dimension of the big vector space, this always means that the subspace is the original vector space itself, which would not be a proper subspace. But proper subspace is more like a definition thing that hopefully doesn't come up. All right, so if I ever get to it, the next thing we'll talk about is some spanning sets. So for any set of vectors in Rn, the span of those vectors is a subspace of Rn. So that means that any subspace of Rn can be spanned by vectors in Rn. So basically, span is like, if we have a group of vectors, what is the set of vectors I can reach if I linearly combine, if I take any linear combination of that set of vectors, what can I reach with them? That set forms a subspace because it's a set in Rn. So it's a subset of Rn, so it'll be, and Rn is a vector space, so it will be a subspace of Rn. And then any subspace of Rn Rn can be spanned by vectors in Rn. All right, so I hope this helps if you are trying to learn what a vector space is at this time. All right, I wish you the best of luck. Have a great day, and